Before every single display in our lives went digital, getting a reading meant watching a real, physical needle sweep across a marked scale. We're talking about those classic ammeters and voltmeters. Today, we're going to peek under the hood of these incredible electromechanical instruments and really see the elegant physics that makes that little pointer move. So let's dive in and find out what makes them tick. So, have you ever actually stopped and looked at one of these things and wondered what is really going on in there? It looks kind of simple from the outside, but inside there is a fascinating, invisible dance of forces happening. And here's the thing, it's not magic, it's physics. And we're gonna break it all down. All right, so here's our game plan. First up, we're going to uncover the 3 core forces that are battling it out inside every analog meter. Then we'll get into the most common type, the PMMC, and figure out why it's a DC-only device. After that, we'll check out the super clever electrodynamic design that finally cracked the AC measurement problem. And we'll wrap up by looking at the almost unbelievable sensitivity of the galvanometer. Okay, so it turns out at the very heart of every single one of these instruments, there's this constant, balanced tug-of-war between 3 separate forces. And if you can understand this little battle, you'll understand exactly how a flow of electricity gets turned into a reading you can actually see. It all kicks off with the deflecting force. You can think of this as the engine of the whole system. The moment you run an electric current through the meter, it creates a magnetic effect. And that effect gives the pointer the initial push to get it moving off of 0. And the key thing to remember is, the more current you have, the stronger that push is going to be. And check this out, this is exactly where that push comes from. You see the current, marked with an I, and it's flowing through a coil of wire that's sitting right in the middle of a magnetic field. Well, that current flowing through the coil interacts with the magnet, and that creates a twisting force, we call it torque, that physically rotates the coil. And since the pointer is attached to the coil, well, it moves too. But, just a push isn't going to cut it. Without something fighting back, the pointer would just shoot to the end of the scale and get stuck there. That's where the controlling force comes into play. This is the pull that pushes back against that initial deflecting force. And, just as important, it's what makes the pointer snap right back to 0 when you turn the current off. So what's providing that pull? It's these 2 delicate little spiral springs. As the coil twists, it starts to wind these springs up. And the more they get wound, the harder they try to unwind. They resist the motion. The pointer finally comes to a stop at the exact point where the spring's pull perfectly balances the magnetic push from the current. That point of equilibrium is the measurement. Okay, so we've got a push and a pull. We're good, right? Well, not quite. Now we've created a new problem. With just those 2 forces, the pointer would act like a pendulum, just swinging back and forth and oscillating around the right answer. To make the meter useful, we need a 3rd and final force, the damping force. This is the settle down command that makes everything stable. And this chart shows you exactly why that damping is so critical. See that wavy, dotted line up top? That's what happens when there's no damping. The pointer just wiggles back and forth forever. You could never get a reliable reading. But now look at that solid line. With the right amount of damping, the pointer zips right up to the correct value and just stops, dead still. That's the difference between a useless gadget and a practical tool. Okay, now that we know about our 3 forces, let's see how they all work together in the most common type of analog instrument ever made, the permanent magnet moving coil, or as everyone calls it, the PMMC. This thing was the absolute workhorse of the analog world. The way a PMMC is built is just beautifully simple. First, you start with a strong permanent magnet. Then, you place a soft iron core right in the middle to concentrate the magnetic field and make it nice and uniform. After that, you put the moving coil on a pivot right in that magnetic field, so it's free to spin. And finally, you bring back those spiral springs we talked about. They actually do 2 jobs at once. They provide the controlling force, and they act as the tiny wires that carry current to and from the moving coil. So efficient. Now we get to the PMMC's one big weakness, its Achilles heel. Because it uses a permanent magnet, that magnetic field is totally fixed. North is always north and south is always south. That means the electric current has to flow in one specific direction to make the needle go up. If you hook it up backwards, the force is reversed and the pointer tries to bend itself around the 0 pin. That's why we say it's polarized. It's a DC specialist, and DC only. So let's just quickly sum it up. On the plus side for the PMMC, its scale is perfectly even or linear, which makes it super easy to read. They're also simple and pretty inexpensive. But on the downside, the big one is that it's polarized. It's a DC-only instrument. It can also get thrown off by other strong magnets nearby. That DC-only limitation is a huge problem. So what do you do when you need to measure AC?
Well, to measure alternating current, engineers had to come up with a whole new trick. And that trick is the electrodynamic instrument. It basically takes the PMMC design and makes one absolutely brilliant little change to completely solve the AC problem.
So what was this brilliant change? They just threw away the permanent magnet. That's it. Instead of a fixed permanent magnetic field, they used another set of coils, fixed coils, to create an electromagnet. This means the magnetic field is now being created by the very same current that's flowing through the moving coil. And this is where the design is just pure genius. See, AC current flips its direction back and forth, right? In this meter, when the current reverses, the polarity of the fixed coil's magnetic field reverses, but at the exact same time, the polarity of the moving coil's magnetic field also reverses. It's like multiplying two negative numbers. You always get a positive. The pushing force, that deflection, is always in the same direction, giving you a steady reading from a current that's going completely wild. Of course, like always, there are trade-offs. The huge advantage is that it measures both AC and DC no problem. But because the force is now based on the current squared, this scale gets a little weird. It's all squished together at the low end and then spreads out at the high end. These guys are also usually less sensitive, and the frequency of the AC can sometimes affect the reading. Okay, let's shift gears now. We've been talking about measuring current, but what if your goal isn't to measure, but to simply detect the absolute tiniest, faintest trace of a current? For that, you need a specialist. You need the galvanometer. It's designed to hear the faintest whispers of electricity. And when I say faint, I mean it. To give you an idea, a really high-quality galvanometer can show a full swing of its needle with a current of just 2 microamps. That's 2 millionths of an amp. It's just an incredibly, incredibly tiny amount of current. So at its core, a galvanometer is really just a PMMC that has been tweaked and optimized for maximum sensitivity above all else. Its main job is often to be what's called a null detector. That's a fancy term for an instrument that's just there to tell you if the current is exactly 0. It's all about detecting presence and direction. To do its job, it has a few special features. Since it needs to show you which way the current is flowing, its 0 point is right in the middle of the scale. The needle can swing left for a negative current or right for a positive one. And for the absolute peak of precision, some of them get rid of the physical needle entirely and instead use a beam of light as a pointer. This totally eliminates reading errors from looking at the needle from an angle. And speaking of that, here's another super clever trick to make sure the readings are accurate. See that little mirrored strip on the scale right behind the pointer? To get a perfect, error-free reading, you're supposed to move your head until the real pointer completely covers up its own reflection. The instant the reflection disappears, you know you're looking at it perfectly straight on. No more parallax error. So simple, but so effective. So, we've seen this incredible, elegant dance between deflecting, controlling, and damping forces. We've seen how a simple design change, swapping a magnet for a coil, can solve a huge problem. But this all kind of leads to a final question, doesn't it? In our world of instant digital readouts on everything, why do these fundamental analog principles still matter? What can we still learn from the simple, beautiful mechanics of a moving pointer?